Hiroshi, if you see, because yes, please.
Quantum gravity people often begin their talk by saying that they are 200 people and so on. How you estimate the number of people working in string theory?
I don't know. I have no idea. The question was that actually the number of population of string theory community, which I have no idea.
Okay, if there are no questions, let's thank Hiroshi again for this very nice. Okay, I think our next speaker, which did touch experiments, it's very appropriate for him to close the session. So please, David.
Well, it's customary, and I will thank the organizers for arranging such a wonderful meeting. I think we all enjoyed it enormously. It was very well done, and especially I liked the wonderful review talks we had at the beginning of each day. However, it's also customary to thank them for giving one the honor of speaking, and I'm not going to thank them. It would have been nice to just enjoy the talks and the wonderful summary that we just heard without having to think of visionary remarks. And so I decided to be totally revolutionary and not use any visuals. No PowerPoint, no transparencies, no Blackboard. The real reason is I didn't have time to prepare a talk. But it's a challenge. And so at the KITP, many of you know we have this Blackboard seminar tradition. And I once heard Doug Lynn, who is an astrophysicist, rise to the challenge of having to explain to a bunch of string theorists, condensed matter theorists, all sorts, the theory of planets without using transparencies and all the beautiful pictures that astrophysicists usually show. So he gave a talk standing in one spot, just using his hands with no other visual aids. It was, talking about stability of planet orbits and formation of planets and everything. It was a tour de force. I can't even approach that, but anyway, that's my excuse for not giving you such a beautiful presentation as we just saw from Hiroshi. I guess Eliezer regards me as one of the few of the old or ancient generation that still remembers what it was like to confront theory with experiment. That brought me back to my first memory of CERN, which was almost 40 years ago. This conference began with Gabriele talking about 40 years of string theory. 40 years ago, beginning of string theory was when I first came to CERN as a postdoc. Chris Llewellyn-Smith was here, Alvaro was here at the time, Julius West I met, Mary Kay Gare. I was CERN was a vibrant center of theory. It was not the center of the experimental world in particle physics. There were many centers, and from my point of view, SLAC was the center. That's where they were discovering really fascinating things that I was most interested in. Although I was also interested in string theory. While I was in CERN, I wrote my first paper on string theory called Generalizations or Satellites of the Easily Forgettable Attempt to Generalize Veneziano's formula, which was still not at all understood to generalizations. I discovered it was not easy to generalize string theory, and it was a total failure, but it was a wonderful period of theory at CERN and experiment. And it's really nice to come back 40 years, well, it's nice to reflect on those 40 years and how CERN has survived for 40 years and is flourishing, and how string theory has survived for 40 years and is flourishing. It's quite amazing. That's a lot has happened. And when we look at particle physics and particle theory around the world, we realize how remarkable both survival stories are. There aren't very many labs in high-energy physics that have survived. In fact, we face a world where only one might survive, and it's here. And all our hopes will depend on its success. And it looks also like we face a world where only one umbrella, theoretical umbrella in fundamental physics will survive, and it's string theory, and it's eaten up everything else. So we have string theorists like Andre Linde here, and string theorists like Lance Dixon here. I mean, it's true that we haven't absorbed yet loop quantum gravity, but I'm not sure we want to. And we now know that string theory will never be killed because it incorporates the standard model, right? It is gauge theory. Its standard model will always be here as a damn good approximation to the real world. So, but if you go back and think about it, it is amazing what's happened in 40 years, not just as surviving as a candidate in Hiroshi's language, which I really like, but also becoming, having enormous demonstrated success as a model of quantum gravity and of a unified theory, as an increasingly powerful tool for standard model physics, for gauge theories, now for condensed matter physics, for mathematics, in ways that nobody could ever have imagined way back then, 40 years ago, when it was a ill-understood candidate for describing the nuclear force. So that's sort of my most optimistic remarks, in a way. I have no doubt that this will go on. What about this meeting? Well, this meeting has been like many of our meetings, like all of the string meetings I've been to, enormously exciting. So one sits here and just listens to talk after talk, which blow your mind. However, of course, I think we all agree that unlike a few of the strings conferences, there haven't been any great breakthroughs, any revolutions. There are a few mini revolutions, or as Jeff Harvey said, insurrections. But remarkable progress on many, many of these fronts. String theory, it's really, I think some of what Hiroshi said at the end was very interesting, this large tent, which we call string theory. When I explain to people who don't understand how CERN, how modern experimental particle physics works, they can't understand how you can do an experiment with 2,000 collaborators. And I'm not sure I can understand it either, but I explained to them that it's not, it's not one experiment, it's a whole world of experiments. And to some extent, string theory is equally diverse. Even though it has one name, it has all of these different aspects. And the insurrections or new remarkable progress we've heard here has been on many of these fronts. Now, Hiroshi did such a marvelous job of summarizing all of this. I'm just going to point to the things that struck me particularly, and not in any particular order or order of importance. The first thing had nothing to do with string theory. It had to do with the LHC. I mean, it was great to come here and to see this machine almost ready to begin in a week or two, and to provide us with real data in the coming years. So that's enormously exciting. It's nice to see it and feel it in this laboratory. And, okay. Then, as far as string theory goes, the remarkable progress in gauge theory, calculations that we've heard about, which owe their success to both to string theory and to gauge theory. They were beautifully reviewed and discussed with enormous progress. I must say the thing I found most fascinating was the explanation. One of the things I found most fascinating was the explanation of this dual conformal invariance, which was already there in Alday and Maldesena's work last year, but fermionic T-duality is one of those things that obvious once you just have to say the word, give the title of the talk, and many of us could have discovered it. So that is always admirable and beautiful, and I'm sure will lead to much more in the future. These calculations are really amazing, and together with the unbelievable advances in the integrability, in the use of integrability to calculate the closed string sector of n equals 4 super Yangmills theory, does give us confidence that we will solve n equals 4 super Yangmills theory in the planar limit. Matthias even argued that he could see a solution, an explicit solution of the full Yangmills theory for n equals 4 in the next decade. That's a really optimistic and probably unlikely, but solving the planar limit would be amazing, and it looks like we're really close to it. Maybe in Rome, maybe in College Station. In particular, the calculation that Yannick did of the Konishi operator, anomalous dimension, was really stunning and beautiful. And then, of course, there's the insurrection of the Lambert-Bagger, Gustafsson, ABGM theory of M2 branes, which is just beautiful, and will give clearly another whole area for many of you to work on and produce hundreds of papers, which will be discussed in the next 2 years, and many possible applications to dual theories of four-dimensional gravity theories, which would be very interesting, condensed matter physics. A lot of work, a lot of tools and applications. The continual progress and in detail in phenomenological or string theory or attempts to make string theory a predictive or at least imitative candidate for the real world is remarkable. It's nice to see Qumran turning into a phenomenologist from the bottom up. Lovely stuff about black holes and supersymmetry breaking and applied string theory. String theory is a tool to new areas like Rick physics and condensed matter physics, which hasn't been discussed much here, but I think some of that will come shortly. Then there are things that weren't discussed here. which is also an indication of where we are. There was not one talk really on string field theory. The only talk on the anthropic history, anthropic interpretation of the universe was relegated to the after-dinner speech. So I don't have to talk about that. And I won't. But a question that was discussed, but I don't think answered very well, was what do we actually hope to learn from the LHC? So as particle physicists, we know we're going to learn a lot. We're going to learn about physics and a whole new range of energies. The relevant range for the electroweak, for the Standard Model, for answering many questions about the Standard Model. We will confirm, once again, the Higgs mechanism, maybe in detail now, finally. And we will discover supersymmetry. At least I have a lot of bets riding on that. But you know, it wasn't the question I was asking. As particle physics, we discover supersymmetry. That's big, that's enormous, that's great. But what are we going to learn about string theory from the LHC? And there, unfortunately, it's not clear that we're going to learn enough. I mean, learning that supersymmetry is a property of the real world will be extremely important. Supersymmetry was one of the first things discovered in string theory. And it's an integral part of string theory, clearly. So that'll be spectacularly important, but it doesn't really answer the deep questions or give us a real proof or any solid evidence that string theory as a candidate is correct. We could be lucky that we produce black holes, and or stringy resonances, that the string scale, gravitational scale, is very low energy. I think that's extremely unlikely. I think the most likely miracle that nature owes us, and nature owes us some miracles, is that we'll find something totally unexpected, which is what the experimentalists really expect, of course. And then we'll realize quickly that totally unexpected feature that we weren't smart enough to think about was an obvious prediction of string theory. But this was sort of almost our last chance. And theorists, smart as they are, don't often make their obvious predictions ahead of time. In many fields, like about the quantum Hall effect, the quantization of the quantum Hall resistance was obvious to all condensed matter theorists once it was discovered. And it only took a few months before they explained it obviously. But even then, they weren't smart, or they didn't predict the quantized quantum Hall effect, which was tougher. So I'm sure we're going to, we might very well be in that same situation, which is my most optimistic hope for what will happen at the LHC, that to give us strong clues as to string theory as a candidate for the real world. So now I want to just be a bit critical of string theory. String theorists, in a sense, when you are working, the strategy for most string theorists to pursue understanding of string theory as both as a candidate and as a tool and as a language, and what was the other one? As a model, have been following the time-honored lamppost strategy. Find a new lamppost and explore it. And we have an incredible variety of lampposts, places where we can make progress because of extra symmetries or new ideas. 1,000 points of light. And that's one of the problems, because there's very little work on connecting all these little points of light. And a lot of concentration. They're really lasers, not old-fashioned lampposts. Some of the, and I just wanted to remind you all about the need to develop new points of light and move away from those lampposts. What would I have liked to have heard at this conference that I didn't hear? Well, I think some of the issues that weren't addressed, I'll mention 3 of them. And urge some of the younger people especially not to just concentrate on the lampposts, but go out, wander off into the dark. Very few people are out there in the dark, less competition. And so one of the things I would have liked to have heard is an alternative to the anthropic principle, which we all know is wrong, right? But to really prove that, we should come up with some other ways of explaining the cosmological constant. So, people have crazy ideas. Hiroshi said, but I haven't heard enough crazy ideas about alternatives to the anthropic explanation of the cosmological constant. Could be because there are none, right? But I don't believe that. The other thing that was discussed here by a few people, Simeon and Gabriele Veneziano, were issues about time dependence in string theory. There's very little time dependence. It's so much easier to discuss stationary points and all of those beautiful lampposts, but they don't tell you much about some of the deepest questions that one faces in a quantum theory, high energy scatter. It's amazing after all these years. That's a natural limit which we don't yet understand at all. Very little cosmology. So no one's really looking around. There aren't any good lampposts, I think, yet. But then there's the big issue, which I keep going around asking my friends here and getting totally inadequate answers. What is string theory? So everybody's testing ADS-CFT. And at this point, I think we should just take it. It is true. There's no need to test it. We should use it. Test it. We should all admit that there's absolutely no value for any more tests. It's true. Nobody has any doubt that it's true. But so you actually, all these calculations that people present as if this is another test of ADS-CFT, you should really think, well, what is this test good for? It's not a test. It's true. You want to use it. And of course, it is an incredibly powerful, it's the most powerful tool that we have in the toolbox that Hiroshi talked about. And it is useful for standard model, gauge theories, condensed matter physics, and so on. But can we use it to answer the question, what is string theory? So ADS-CFT, which is so powerful, is a duality between 2 ways of describing string theory. One is strings propagating in some background space, et cetera, and one, the holographic dual gauge theory. And both sides of that that duality are very non-trivial, but not impossible. So it's a wonderful duality because you have to compare 2 rich structures. We have other dualities which aren't as powerful because one side is trivial and the other side is complicated. For example, where string theory started, the theory of strings moving in flat space, which is dual to something, maybe discrete light cone quantization of matrix theory. a very nasty dual theory, which is almost impossible to work with, is rather ill-defined. So there's a duality between something which is absolutely trivial, and we understand that the classical limit of that string theory. That's the Veneziano formula, its generalizations. We have explicit solution and a very complicated. We've had that for a long time. Useless. In that case, where one side is solved in the classical limit, trying to answer what is string theory led to string field theory, which still isn't much of a tool. There were no talks on string theory, field theory at this conference. So the reason ADS-CFT is so useful is that both sides are complicated, and you can do a lot of work trying to solve both sides. And now imagine we've solved it. So by next year, there's a solution of maybe even from both sides. We have completely calculated the spectrum of strings propagating in ADS 5 cross S5 using the integrability of the string theory, and we have completely solved, or we do this simultaneously, n equals 4 gauge theory in the planar limit. Very good tool, but is that a solution of string theory? No, it's a classical solution of string theory. On the gauge theory side, we might imagine, we know that that theory exists even at the non-planar level. We can imagine calculating 1 over n corrections. We can even, like Matthias, dream of an explicit quantum solution, a finite n solution of gauge theory. Is that a solution of string theory? Well, if you think about it, if you had the gauge theory totally under control, or just totally under control in the planar limit, the way you would go about defining or constructing string theory in a way that is background independent, that might encompass what string theory is, would be to deform it. You'd want to be able to go from a ADS 5 background to flat space. In the gauge theory language, that would mean adding higher dimensional operators that change, that affect the move the horizon, move you away from the horizon. So you get into, if you really think about moving away from that background, you'd be confronted with deformations of the supersymmetric Yangmills, the conformally invariant supersymmetric Yangmills theory, by adding non-renormalizable terms, and all hell breaks loose. Very similar to the way, on the other side, if you solve the string theory exactly, like in flat space, and you try to define background-independent definitions, you are led, say, in the case of open string theory, to discuss all conformal field theories. Both are impossible, it seems. And we don't know what it would mean to discuss the space of the Wilsonian space of all gauge theories, moving away, deforming them by non-renormalizable operators. We have some hints from non-commutative gauge theory that there are directions where one can move which are quite safe. And presumably, since string theory exists in flat space, there is some way of moving away from gauge theories, from this gauge theory dual to string theory and ADS to flat space. How would you do it? Even if you had an explicit solution before you of the starting point. So that's trying to put a little more meat on the question, what is string theory? Which is sort of at the heart of knowing what it would mean to come up with a real candidate. String theory as a candidate would require understanding which of the infinite or enormous number of solutions of string theory we have, even though we don't know what the equations of which they are solutions are. So anyway, those are three of the issues I would have liked to have seen discussed, and will still remain even if we have a final proof of ADS-CFT or any of these other dualities. Anyway, I don't want to end on a pessimistic note. In fact, those complaints, and we're not pessimistic. It's fantastic that we have such great questions remaining, not just technical advances, but deep conceptual questions. And the history of this field assures us that it will remain rich and exciting with progress equal to that reported this year, next year, and forever for quite a number of years. But once again, most important and appropriate for this place is that we're assured that we're going to get some hints, and maybe crucial ones, from nature. Thank you.
First,
I have one more task, which is...
they're not here yet, I think.
So I'll drag it up. Which was to thank, but of course the organizers have been thanked many, many times. And
please don't leave, we are waiting for the...
Thank the people who did the real work, who are on their way to get a...
I hope.
So we should wait.
Yeah, fine. Okay.
So Elena, Amani,
Okay, and I think the last thanks is Andrei. Is Andrei here actually? Yes, as Andrei said, I think we can thank all the speakers which really gave great talks, and you for being here. So thank you.